Hello, my dear student. This is Manish Academy of Education. We will learn the point 7.6 of lesson number 7 of standard 12th sem first. AC voltage applied to a series LCR circuit. Here it is given LCR, inductor, capacitor and resistance. We know that here applied voltage is what? AC voltage. V equal to V m sin omega t. Now if Q is the charge on capacitor and I is the current at time t, we have by the Kirchhoff loop rules, total voltage V, AC voltage V is equal to total sum of voltage across resistance R, inductor L and capacitor C. It is written here L di by dt, voltage related inductor, IR, voltage related resistance, and Q by C, voltage related capacitor. Now we want to determine the instantaneous current I and its phase relationship to the applied alternating voltage V. We shall solve this problem by two methods. First, use the technique of phasor method, and the second method we solve analytically to obtain the time dependent of current I. Now we use here phasor diagram solution first of all. We know that from the figure we see that the resistor, inductor and capacitor are in series, and therefore the AC current in each element is the same at time. It is also we have studied in series and parallel connection in 10th also. Now having the same amplitude and phase, let it be I equal to Im sin omega t plus approach. Approach is the phase difference between the voltage across the source and current in the circuit. On the basis of what we have learned in the previous section, we shall construct a phasor diagram for the present case. I be the phasor representing the current in the circuit as given by figure. And now further, let VL be the phasor voltage across inductor, VR be the phasor voltage across resistance, and VC be the phasor voltage across capacitor, and V be the total voltage across the all inductor, resistance and capacitor. And the source respectively from previous section, VR is parallel to I, VC is pi by 2 behind I. It means voltage related with capacitor is behind pi by 2 with respect to I, and VL is pi by 2 ahead of I. It means voltage related with inductor is pi by 2 ahead of I. So VL, and VC and I are in figure with appropriate phase relation. Here we can see VR, VL and VC, and here omega t plus approach phase angle. So the length of phase, the length of these phasors or The amplitude of VR, VC and VL are denoted by VRM is equal to IMR. Then VCM equal to IMXC and then VLM equal to IMXL. Whatever we have studied in different part. Previous point. The voltage equation for the circuit can be given is equal to or written is equal to total voltage across inductor, total voltage across resistor and total voltage across capacitor, and add them and we will get total voltage V. So the phasor relation whose vertical component gives the above equation VL plus VR plus VC equal to V. Now the relation is presented in figure 7.13b. See here, this figure. VC and VL are always along the same line. VC and VL are along always the same line. VC and VL. So here it is written. These things VCM minus VLM we have studied in previous chapter 11th vector. So it is written here VC minus VM. It is the resultant of voltage or a voltage result, final voltage result. So now by discussion, again we will read it. Okay, this relation is represented in figure 7.13b since VC and VL are always along the same line and in the opposite direction. Also we have studied with respect to only capacitor connected with circuit and only inductor connected with circuit. So in this both two topics we have studied these things. Both are opposite. Now they can be combined into single phasor. It means VL plus VC. It is written here. Now by use the Pythagoras theorem, Vm square equal to Vrm square plus Vcm minus Vlm whole square. Now here we will put the value, substituting the value of Vrm, Vcm and Vlm in the form of Im, Xc, XL. So here total voltage V square M equal to Im R square plus Im Xc minus Im XL square. Now Im square is the common. So final answer Im square and in bracket R square plus Xc minus XL whole square. And from this we get Im equal to what? Im equal to Vm upon under root R square plus Xc minus XL whole square. And by analogy to the resistance in a circuit, we introduce the impedance Z. So these things is denoted by impedance Z. And now we can write Im equal to Vm upon Z. And we know that Z equal to under root R square plus in bracket Xc minus XL whole square. Since phasor I is always parallel to phasor VR and the phase angle phi is the angle between VR and V, and it can be determined from this figure. Tan phi equal to opposite by adjacent. Adjacent by opposite. Sine by cos. So here VCM minus VLM divided by VRM. And now put the value in the form of XC and XL. So tan phi equal to XC minus XL divided by R. Now equations 7.26 and 7.27 are graphically shown in the figure 7.14. This is called impedance diagram, and which is a right triangle with Z, its hypotenuse. Now from the equation 7.25a gives the amplitude of the current and 7.27 gives the phase angle. With this equation 7.21 is completely specified. Suppose if XC is greater than XL, XC is greater than XL, then phi is positive. Phi is positive. And the circuit is predominantly capacitive. Circuit is predominantly capacitive. If XC is less than XL, phi is negative and the circuit is predominantly inductive. So, as a result, the current in the circuit lags the source voltage. As a result, the current in the circuit lags the source voltage. Now, from the phasor diagram and variation of V and I with omega t for the case XC greater than XL. XC greater than XL. So we can see here it is the voltage, it is the current, and voltage is at a phi angle. This is omega t1. So from the figure we can see that we have obtained the amplitude and phase of current for an LCR series circuit using the technique of phasor, but this method of analyzing AC circuit suffering from certain disadvantage. So we know that by phasor there is some disadvantage. AC circuit will experience some disadvantage. First, the phasor diagram says nothing about the initial condition. What means? Phasor diagram is not able to denote the any information about initial condition. One can take any arbitrary value of time t, say t1, and draw the different phasor which shows relative angle between the different phasors, and the solution so obtained is called the steady state solution. Steady state solution. And this is not a general solution. Additionally, we do have transient solution and which exists even for v equal to 0. And the general solution is the sum of the transient solution and the steady state solution. After sufficiently long time, the effect of the transient solution die out and the behavior of the circuit is described by the steady state solution.